Okay, today's lesson is going to be inclined planes. This is based on worksheet number 4. This will be put up on Schoology with the link to YouTube. So we're working here today, Wednesday, 11/11/2020, Mr. Dahlstrom's pre-AP physics class. Okay, yesterday what we had worked on in class was forces at an angle. So this was something where we had, for what we had yesterday here. We had a block that was moving horizontally, though its applied force was at an angle. So we may have forces up and down the y direction or side to side. There's video already posted there. So today we're not looking at angled forces or friction. We're looking at inclined planes. What we mean by inclined plane is that, for example, if we have a triangle here, you have an object that is either sliding down or sliding up the inclined plane, either in that direction or it could also be in this direction as well. So if it's sliding up the inclined plane, that means there has to be an applied force or something, or a tension force that's pulling it up. So we're gonna use that data to look at this problem here. So the math won't, once we get to the once the free body diagram is drawn, the math should be pretty straightforward. You should be able to get it from that point. The trouble is understanding the free body diagram and I guess why we can actually do what we're able to do here. So the directions are sort of simple. And it says draw a free body diagram, rearrange the axis. This will be an important thing later. Write the equations x and y direction like we always have. So if there's enough in the x, we solve in the x. If there's not enough in the x, we go to the y. And then we also have, remember, we have our coefficient of friction, which is this divided by that. Friction divided by normal force. Remember also right minus left equals ma of x, and up minus down equals ma of y. Okay, so this has a little story to it, and we're going to kind of break off away from this to kind of go over some of the theory in the free body diagram. We'll go ahead and read it. On a snow-covered roof, a chunk of ice with a mass of 22 kilograms breaks off from the rest of the ice and starts to slide down the roof, which has an angle of 40 degrees. So it has an incline. So here's flat. It has an angle of 40 degrees. The coefficient of friction, mu, between the ice and the snow roof is 0.1. Pretty small, but it is ice. Maybe it's melting ice. And I say refer to picture. There's no picture here, but let's we can kind of imagine, just even if we had, this is our little house here, that we have a piece of ice that's at the very top is basically just starting to slide down that. So that's kind of a picture of what we're going on, but we'll draw a better one here. And I'm actually going to, I'll use this here. So, okay, so that is theta, and then we'll have our block on top. Okay, and it is sliding down, so it will be accelerating in this direction, and that may give some of you pause because you're saying that's not good. It's accelerating down. It's now accelerating down and to the right at the same time. And you said, Mr. Dahlstrom, we're going to try to avoid that, and yes, we are. We are going to try to avoid that. So this is the help of actually drawing the free body diagram away from this, because this can get pretty complicated when we have our forces drawn on that. So what is commonly done is to draw the box over here, but not drawing it like a square traditionally, but draw literally like you're taking this and you're putting it right over there and then making that a bigger drawing so we can see the forces that are going on. So I try to draw it at the same angle as that, just realizing that this real lightly, that's the surface represented here. Okay, so we'll go ahead and draw the forces that we have here. We're still going to use this little center, circle center here. We think, do we have the force of gravity? Yes, we have the force of gravity, which is always sort of straight down compared to where the ground is. So I'm going to draw that extra big just so I can give myself some room when I'm doing this. Remember, that is mg by itself. We do have the normal force. The normal force is always perpendicular to the surface, and it's causing the block to not go through, so it has to be pushing away from it. So perpendicular in a way would be this right there. So that's the normal force. And we do have friction. If we do problems that have friction, then it's going to be a lot easier when we have problems that don't have friction. So might as well do the friction ones. Friction always opposes the motion of travel. In this case, it's sliding this way along the, or I guess in this direction, down the incline. So it needs to be in the opposite direction, and it needs to be parallel to the surface. So back in that direction is our friction force. We're neglecting air resistance. We don't have any tension. There's no applied force here. So you say, what's causing it to go down the inclined plane? Well, the gravity is using it, but not all of gravity, and that's kind of the trick here. Now, we talked about this last week, and I'm not sure I created a video on this here. I'm pretty sure I didn't for the people that were at home. This was a problem. We had worked on this, but this is just introduction to the free body diagram. Don't worry about what's over there, but this is basically the setup that we have right now on this. And the reason why I'm drawing this, so the red is representing the y direction, and the x is the blue is the x direction. And what this means so in the force of friction, because if we're defining up and down to be this way and side to side to be in the traditional here, that means that the force of friction, because that's an angle, is not only going to be present in the x direction at an angle, so cosine or sine, but also present in the y direction, where that's usually not the case. Usually the force of friction is found only in the x and the normal force is only in the y. But if we set it up like this, then that means that we're going to have them both in the x and the y direction, and they're going to have angles. Same thing with normal force. This is also going to be in the x and the y direction and at an angle. And even probably one of the worst parts is that because the acceleration is going this way, the block would technically be accelerating horizontally and vertically at the same time, which means those would both. We couldn't say one of those would be 0 and they would have an angle, and that's just a whole lot of mess. Now, force of gravity would be straight down, so that would be easy. But that's a whole lot of mess, and if we can somehow reorient the problem so that we don't have all this stuff at an angle, what we can do, and I'll kind of draw it over here on this. So I have this block here, and I'll draw this there. Draw this extra big. Force of gravity, normal force, force of friction. Is like I said, if we use the traditional that is up and that is to the side, that leaves some problems here. What we can do is we can actually redefine which way we are calling up or which way we're calling the positive y direction. And how we do that is you're basically saying if we tilt this here so that we now kind of consider that to sort of be the problem, then it becomes a lot easier. Or instead of maybe tilting it here, recognizing that we are now going to, instead of calling this y and this x, it helps to draw a dotted line here. We are now going to call this positive y, and we are now going to call that positive x. So that's there. So, or we are reorienting the axis here. So now the positive x direction is along the plane, and the positive y direction is perpendicular to the plane. Can you do that? Yes, you can do it. It's one of those weird things about math. As long as you are being consistent, meaning that we can't change it back and forth inside a problem to make it easier. So we're doing this so that this isn't at an angle, this isn't at an angle, and then the acceleration is not an angle. So basically by kind of looking at it here, the normal force is now completely up, so we just add it. The force of friction is now left, so we subtract it. There is no applied force. The acceleration, even better, okay, is completely along the x direction, which means that is a of x. And if that's a of x, then that means that a of y is going to be 0, and that's very helpful. Okay? However, we can't get away scot-free. We do have the force of gravity now that it's at an angle. And this is sometimes hard kind of conceptually to understand here, but I want to kind of point out with another picture here over that. If we have a flat box here, okay, there's the force of gravity, there's the normal force. Let's just say we look at that. This incline, basically the angle here, there's no incline. This angle is 0 degrees. And what I'm trying to show here is that the angle between the force of gravity and the y direction is also 0 degrees. So, okay, that makes sense. Well, let's look at a scenario here where we have a very slight incline plane. Okay, so we have box there. We have the force of gravity here. We have the normal force now at an angle. And what I'm trying to show here, sorry if it's off camera, we have a very slight incline plane, meaning that that theta right there is this theta right there. If it's a flat line, this incline, if there's no incline here, then that means the force of gravity doesn't move away from the y-axis. As the incline gets bigger and bigger, the force of gravity always faces straight down, but the y direction, because the incline's getting bigger, is starting to move, and so that angle right there is that angle right there. Okay, we can talk more about that, but so that theta right there is this angle right there. That is our theta. As that gets bigger and bigger and bigger and bigger, then so does this, because the force of gravity is always just hanging down. That's the base of the weight. But as the angle gets bigger here, so does the perpendicular angle gets bigger there. Okay, so we go back to this problem saying, well, we need to split this up into the components, and I've been traditionally using that as y, and then this is x. So we're now thinking this is the y direction. So I need to, this is my hypotenuse. Remember, this is the hypotenuse, so I need to create a triangle with two legs that are perpendicular to each other. So the first one is going to be this one, and that's along the y-axis. That is the y component of gravity, or Fg of y. And so perpendicular to that, okay, we're drawing the sides of the triangle. In order to get there, I need to draw an arrow to the right, and that's the x component of gravity, and that's Fg of x. Now, the other important thing we need to figure out, and this is why this discussion is, how do we know, because this is components, which means we're going to be using cosine and sine. We could use the Pythagorean or the SOHCAHTOA to figure out, but there's a really kind of quick, easy way that said, we look at this angle, that's why it's really important we recognize this is the angle here. We look at what axis, the y-axis, or the x-axis, which one is it connected to? Okay, it's connected. Some might say it's adjacent to this one here. So because it's connected to that, that means we're going to be using cosine for the y-axis for this type problem, which means that this is sine on the other side because it is opposite. So sine, SOHCAHTOA. And so it's not only cosine x, sine y, it's whatever one it's connected to. As opposed, let's go back to this one right here, where we had our forces aligned this way. In this one, the angle was connected to the x-axis, so that means the x-axis got the cosine. So you have to be careful of where the angle is being provided here. But now that we have that, if that is our free body diagram, we can go back to our problem here. Okay, if I want to draw back on this, I'll draw this real quick. So understanding that that is the y-axis and that is now the x-axis, we have our Fg of y, and then we now have our Fg of x, and understanding that the angle provided is 40 degrees. So that is our theta. And we are always using whatever angle is provided there. We're not going back like vectors and figuring out what it is for the unit circle and all that. That is a setup of how we figure that out. That's how we draw the free body diagram. So we're not necessarily going to solve the problem, but I'll write out what the x and the y direction equations are, and you should from there be able to figure out how to solve this. So what we're trying to figure out is what is the acceleration of the chunk. And since we have reoriented our axis so that now this is positive y and this is positive x, we're trying to figure out what is a of x because it's sliding completely this way, and remember that tells us that a of y is 0. Okay, so if it helps to turn it to look at it, you can do that, but obviously we're writing our equations here. So I don't want this video to go a little bit too long. So the sum of the forces in the x direction, all the forces right, and remember we are redefining right to be this way. So all the forces right would be Fg of x, so it's pointed to the right, so Fg of x. Okay, nothing else is to the right. We don't want to accidentally use this because it's not completely up or down or side to side. We used it to understand what this is here. Okay, minus all the forces to the left, which in this case is the force of friction, equals our mass times the acceleration in the x direction. Now reminding ourselves, remember we figured out on the other page, because this angle is connected to this axis, that one is the one that gets cosine, so that means that one gets sine. So we can simplify this a little bit further. Remember, this is our equation right here. That is our equation. So f of g is really mg. X, because it's opposite, it's not connected to, we are using sine of theta minus the force of friction equals ma of x. Okay, so there's there's the basis of that. Okay, we may have enough information, we may not have enough information, so we'll now write the equation in the y direction. Because based on the worksheet, which I'll post in Schoology, there's enough information for you to figure out what's going on there. Now we're looking up minus down. Okay, so remember this is now up, so up is the normal force. Minus down, we don't want to confuse this as down. We reoriented down to be this way, so that is Fg of y, so minus Fg of y. No force, more forces up or down. So that equals the mass of our object times the acceleration in the y direction. And one of the whole reasons that we change the axis is so that would be 0, and that's very helpful to us because that means that whole side over there is 0. So F of n minus, remember force of gravity is mg, and the y direction, it's connected to the angle, so that gets the cosine of the angle equals 0. So that really, I guess we're saying that right there is our equation, but that should be enough for you to figure out. If we figure out if we realize what we have in these problems, we're given the mass, we know the gravity, we're given the angle, we're given the mass. So we don't know the force of friction, the acceleration, but we've done problems where we get around that. So if we don't have enough here, we go to the y direction. We know the mass, we know the gravity, we know theta, so there's enough for us to solve for the normal force. And remember, there's a third equation that we have here. If we have friction, it's the coefficient of friction is the friction force divided by the normal force. Okay, if we can figure out, what that is, which we can, that can go right there. We are also given this, and so the end around way of solving this is that once we solve for the force of friction here, that force of friction there goes right back into there. So we can solve for the acceleration. So it's an end around type problem. So when I say the hardest part about setting these problems up is understanding how this free body diagram works here. Once we find that acceleration, there's an extension problem here where I ask you to figure out the final velocity of the chunk when it slides down. It says if the chunk broke off from the top of the roof and slid down the entire length of the roof, which is 3 meters, how fast will the chunk of ice be moving when it leaves the roof? Well, we can use the fourth equation, or that's the fourth equation there. And if we solve for that, Vf equals Vi squared, and that's, if it's going from rest, that's 0, plus 2 times A, and in this case that's A of x times delta x, which is what they give us. So you can figure out what the final velocity is by calculating that. Okay. I'm going to go ahead and stop this video here. I am going to set up the other side because it's a little bit different. The other side is the same scenario, except now we have it going down. This is actually one of the first problems we have moving in the negative direction, so getting used to that. So I'm going to create one more video and just kind of show you a little bit quicker how to set it up on the other side here. So I'll post this in Schoology as soon as I can. Thanks.